Number 111. A compound with a molar mass of about 42 grams per mole contains 85.7% carbon and 14.3% hydrogen. What is its molecular structure? Okay, so at the end of the day, the question is asking for a molecular structure. And a molecular structure is just a fancy way for saying the molecular geometry. I mean, is it that fancy? I guess it's the layman's term, right? But either way, molecular structure, molecular geometry, finding the shape of the compound, that's what we're looking for. Whether this is tetrahedral, trigonal planar, trigonal pyramidal, bent, right? Those are all of your molecular geometries. But the idea here is that, do we even have a compound? No, I don't see one, right? The only thing that they basically gave us was the molar mass of the molecule, and that this molecule contains 85.7% carbon and 14.3% hydrogen. So, strap in those seatbelts. We're going for a little ride. Anytime that we see percents, right, especially if it's percents from elements, we always think of the whole flow that I wrote down here, right? We can always go from a percent of an element to find out its grams, to get the moles, to get the mole ratio, and then that's how we get those formulas. So whether it's an empirical formula or a molecular formula. And from the molecular formula, we can find the molecular geometry. So molecular goes with molecular. But we're all the way at the beginning. Oh boy. So let's just run it through, right? We're doing a little bit of stoic, right? Math. And then we can transverse into the Lewis structure, molecular geometry idea of it. But let's go. So they told us that we had 85.7% carbon. And then I'll drop down here. I'll say we have 14.3% hydrogen. Now just make sure that there's no hidden percents, because sometimes they'll, tell you 3 elements, but they'll only give you 2%. But I'm looking here, and this equals 100, right? If we did 85.7 plus 14.3, we have 100%. So we are good to go. Now, we're starting off with percents. We need to find out the grams. But this is a assumption step, right? We can assume that the sample that we had, right, 100%, we could assume that the whole entire sample was 100 grams. And if the whole entire sample is 100 grams, that means that the percent that you had will equal the grams, because you're just saying that out of 100%, you have 100 grams, so the percent equals those grams. So 85.7%, we could say, hey, we have 85.7 grams of carbon. 14.3% hydrogen, we have 14.3 grams of hydrogen. And now, just like before, you add this up, it equals 100 grams, that's the percentage. So the first part, check. Now we have grams, but we just got to go to moles. We know how to do this, right? Grams to moles, we've been doing this for a long time now. Grams to moles, we always use the periodic table, right? So I'll say PT, periodic table. And remember, 1 mole of any element or compound, right, or molecule, always equals the grams of that molecule. So I'm just labeling it as X. So if we do it the dimensional analysis way, right, just to kind of get, familiar with dimensional analysis, we never want to lose it. Grams of carbon, you don't want that anymore, so that goes on the opposite side to cancel out that unit, grams of carbon on the bottom, and mole of carbon up top. 1 mole equals whatever the mass is of carbon. And on my periodic table, it says 12.01. Can you round to 12? Most certainly. You'll get the same general answer at the end of the day. Okay? So grams cancel out with grams, and we're left with moles. Now for this, I like to run through every one first before I go on to the next step. So I'm going to find the moles for hydrogen as well. So grams of hydrogen, that goes on the bottom, and we get moles of hydrogen, that goes on the top. And 1 mole of hydrogen, on my periodic table it says 1.008 Can you round this to 1? Most certainly. You'll get the same answer at the end. Grams cancel out with grams. But let's just see. We'll go more specific. So we'll do 85.7 divided by 12.01. Just checking to see the numbers look good. They look good to me. So we'll say that this is roughly about 7.1, I guess, 14 moles of carbon. And then, I mean, this is going to be basically 14.3 divided by, it's going to be roughly, I mean, the same number, right? 14.2. Or we'll say 14.19 if we have the same placement. It doesn't really matter. 14.2. Okay. So now, this step is done. Now we have to go from moles to a mole ratio. Now keep in mind that ultimately we can find an empirical formula from this ratio. An empirical formula is always the lowest amount of moles. So with that idea, we make a ratio by always dividing by the lowest number of moles. So between 7.14 and 14.2, the lower number is 7.14. So we just take that and divide both of them by 7.14. This will now, we only have 1 mole of carbon. And this one, I mean, if we do the actual math, it's going to be very, very close. Keep in mind that for this, we generally round to a whole number. And 1.988 is very, 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 very close to 2. So 2 moles of hydrogen. Okay, so maybe I'll just write down here, divide by lowest number. That's all we had to do here. Okay, and this part is done. Now, from that ratio, we can find an empirical formula. All you do is you just put the two together. So if you have 1 mole of carbon, you just have a C. You can put a 1 here, but you don't have to. And if you have 2 moles of hydrogen, it would be H2. And this is the, we'll say, empirical formula. Okay, so this is done. Now, the next part is to find the molecular formula because we want to find the molecular structure, the molecular geometry. This is where we take our molar mass. The molar mass of the compound is from the molecular compound. So, whenever we're doing this next step, we want to find out how much larger the molecular compound is from the empirical compound. So in this case, what we have to do is we just take the molecular mass or the molar mass, because that's from the molecular compound, and divide it by the empirical mass. Now they did tell us that the molar mass, right, the molecular mass, was about 42. So that goes on the top. But now, do I know what my empirical mass is? Not right now. All I know is that I found an empirical formula of CH2. But I can quickly find out what that empirical mass is, because I know my masses of the periodic table. We have a carbon, we have a hydrogen. We got 1 carbon, we got 2 hydrogens, right? And each carbon is 12.01. So 12.01. Each hydrogen, I'm just going to put the actual number that I see on the periodic table, 1.008. So if I times that by 2, I get 1.016. And now, let's just add those numbers up. So 12.01 plus, whoa, good catch, Christina. Hold on. Uh-oh, what happened here? I guess we'll delete it. 2.016. Did anybody catch that? Or are you screaming at me? 2.016. That looks good now. 12.01, 2.016, perfect. Okay, So we get a empirical mass of roughly about 14.026 grams per mole. So that's what goes on the bottom here, the 14.026. And now let's just see how many times larger is the molar mass from the empirical mass. I'm going to take my 42 and divide it by that number. And this is also supposed to be a very, very, very close number. Oop. What happened here? There we go. This is supposed to be a very, very, very close number to a whole number. 2.99 is roughly about 3. Well, what does that mean? When you're doing this math, this means that your molar or your molecular formula is 3 times larger than empirical formula. So if I have a CH2, and now I know that I'm 3 times larger, I take those subscripts and I times them by 3. But you got to be fair, you got to do it to both of them. So my new compound would be C3H, 3 times 2 is 6. So now, let's take all this math that we've done to get to this point and say bye-bye, because we need space. Because now we're going to get the molecular structure. So, goodbye to all of this. Oh no, we have to keep this. Okay, so this is going up here, but everything else, we could say goodbye. We did all this work just to find out that the compound is C3H6. Bye-bye. Okay, so let's just maybe bring this in the middle. We did all that hard work. And now, before we even find the geometry or the molecular structure, right? Always, always, always draw a Lewis structure, because that's going to show you what this compound looks like drawn out. And if you can see it drawn out, you won't have to guess as to what's going on. You can find out if there are any formal charges. You can find out the molecular geometry, any resonance structures, hybridization. There is a lot of stuff that the Lewis structure can tell you. So we're going to take a few seconds and draw out the Lewis structure. Now in this case, we just have a total of 3 carbons and a total of 6 hydrogens. Now, in this case, keep in mind that hydrogen can never be in the center. Hydrogens are always flanked to the outside of the molecule because it could only have one bond. So in this case, my 3 carbons that I have, I know that they're going to be together. So I'll say maybe 1 carbon, 2 carbon, 3 carbon. And now we just have to divvy up the 6 hydrogens, right? Now your placement could be different from mine. It just has to work as far as the Lewis structure, especially when you're getting into multiple atoms here. There could be different orientations of how to draw. But let's just see. Maybe I'll put, I guess maybe we'll put 1 hydrogen here, 1 hydrogen here, and 1 hydrogen here. And let's see, would that even work? I don't know, we're just kind of going with it. That's 3, 4, I don't know, maybe this one needs one. 1, 2, 3, 4, 5, and then maybe I'll put this one over here. Okay. So, keep in mind that hydrogens can only make a single bond, so single everybody up. That has to deal with the hydrogens. So there you go, there you go, there you go, easy. Now, let's work a little bit harder to just get the right bonds for the carbons. But keep in mind, remember, carbon can only have an octet, not an expanded octet. So this carbon has 2, 4, 6 electrons already. It needs to bind with the other carbon, but if it has 2, 4, 6, it only would need a single bond. And now this carbon has the octet. Now let's work with this carbon. This one's only got 2 bonds, 2, 4. So it would need 5, 6, right? 2, 4, 6, so it needs 3 bonds, and 1 more bond to get the octet. 1, 2, 3, 4. And that's okay because this carbon is now happy. 2, 4, 6, 8. It's got 4 bonds. And there we go. And from here now, we can finally find the molecular structure or the molecular geometry. Now, they did not specifically say which carbon to look at, because if you have multiple carbons in your compound, you can have multiple geometries. And that's what's happening here. Now, your teacher or professor may want you to memorize your molecular geometries, or they may be nice and provide them on a test or a quiz. But if your teachers or professors were like mine, you had to memorize them. But I'm going to post it up here. All the molecular geometries are here. What a bunch. Now, in this case, all we have to do is just focus on the different carbons. Now, there's 3, but there are 2 of them that are equivalent, right? There's this carbon that looks like it has 4 single bonds, versus these 2 carbons that have, and maybe we'll do blue. Oh boy, I don't like that either, but I guess it's better than the green. These 2 carbons have 2 single bonds and a double bond, right? This carbon has 2 single bonds and a double bond. So these I can kind of group together because they would have the same geometry. This one, on the other hand, would be a different geometry. So let's give it a shot. Anytime that you are searching for a molecular geometry, the first thing that you need to do is just find out how many atoms is that atom bound to and how many lone pairs. For this carbon, it's bound to 1, 2, 3, 4 atoms. So I'm going to write that down, 4 atoms. And are there any lone electrons around the carbon? Do you see any dots? I don't see any dots. So this would be 0 lone pairs. Whoa. Let's do it for the other ones, right? How many atoms is this carbon bound to? It's bound to the 1 carbon, the hydrogen, and the other carbon. So that's 3. And then if we just look at this one has 1, 2, 3. So they both have 3 atoms. And once again, do we see any lone pairs around the carbons? No. So 0 lone pairs. And that's basically the work that you have to do to figure out where you are in your geometries. What you're going to do is you're going to take your numbers, so 4 and 0, and you're going to add them together. So for this carbon, it would be a grand total of 4. And now, that's my total number of electron pairs. So we are in 4 land. But which one am I? Tetrahedral, trigonopyramidal, or bent? That comes from the lone pairs that you stated. But we already did that work. We said that there was 0 lone pairs. So it's this one, because this one is under 0 lone pairs. So we have a tetrahedral shape, or a tetrahedral geometry, where all the bond angles are 109. When I had to learn it, we learned it as 109.5, but I guess that's teacher or professor specific. And then we do the same for this one. So now we have 3 and 0. We add them up to get a total of 3. So now I'm over here. Is it trigonoplanar or is it bent, right? Nobody really uses angular. No lone pairs, so trigonoplanar. So we have multiple geometries in one molecule, but we got it all covered for. We have the Lewis structure, right? And we have the actual geometries of each of the carbons, and that's the whole question. Whew! What'd you think? I hope this helped. Let me know in the comments. Subscribe to the channel. I look forward to helping you out in more questions. Always keep learning. Keep working out the problems. That's how you guys learn. By constantly doing problems, right? You could read a textbook all day long, and when it comes down to the problems, it might be a little hard to do. But if you dive right in and you do the problems with us, right, and go through these videos, I promise you that it's going to be easier. So just stick with the videos. We are here to help you guys out. We love helping you guys out. And thank you for being part of the community. It's awesome to see how this channel has grown, and it's all because of you guys. So thank you from the bottom of my heart. Thank you from the bottom of my brother's heart. And I'm looking forward to helping you with more videos, or more problems, right? From videos. But anyway, I'll see you later. Okay, bye-bye.